Okay, so this is the last session, and I think the title here is Security and Internet. Our first speaker is Morley Mao. Morley is an associate professor in the EECS department at University of Michigan. She got all three of her degrees here at Berkeley, and her research interests include network systems, mobile and distributed systems, and network system security. And she was PhD number 26.
Thanks, David. Actually, my talk today is going to be focused on finding some kind of rigor in identifying defense solutions for network-based attacks. So before I start, I wanted to just share with you what I had in terms of fun memories working with Randy. So one thing I remember is going to Randy's office and the cute little dog. I forgot his name, actually. This is a border terrier. And Randy sometimes eating his rice cake snacks. And I was wondering, is that enough calories for his lunch meetings? Anyway. So we also had a lot of fun. I fondly remember there was this group outing. We went to the Angel Island State Park, and we had a lot of fun there. And from there, I also started enjoying hiking, doing more outdoor activities. And we have numerous retreats at Lake Tahoe, and this is something like I remember fondly of because we had opportunities interacting with industry researchers and getting feedback. And this is actually something I just retained when I'm doing my research work at Michigan, is trying to interact with industry to get feedback. So this is something I think it was a very valuable experience taking away from Berkeley. So. Another thing I want to say is I remember Randy talking about he oftentimes changed topics and trying to graduate a bunch of students and then starting a new topic. And this is also very inspirational for me because when I started out in doing my PhD work, I was actually focused on the interdomain routing protocol, BGP, at the time. And from after graduation, I moved into looking into more security aspects of routing protocols. And today's talk is mostly about network-based attack defenses. So these days, I'm mostly doing mobile research as well as network system security research. So network-based attacks, unfortunately, are still very prevalent. So a lot of times, people just blame the end system is sort of the culprit because vulnerable software are running there. But it turns out network protocols themselves can be insecure, right? So even though there are these protocol specifications, actually you can prove the specification to be secure, but unfortunately implementations of protocol which are specified, which often leave a lot of room for freedom to implementers to do different things, and oftentimes the implementation may not always exactly follow the specification, even though the specification may be proven to be secure. So our experience is that we also found network information can be abused as a side channel to launch various attacks. So from this line of work, we started thinking about, can we develop more systematic approach to essentially verify network protocol implementations to have better understanding of the guarantee of these security properties we want to have. So that's sort of the main theme of this talk. And I want to start off by saying how we started doing this work is by looking at network protocol specification, and then we started thinking, hey, let's look at TCP. It's a well-studied sort of old protocol, but interestingly, we still found opportunities to break into TCP by injecting traffic into an existing TCP connection. And in the particular case, we found this vulnerability has to do with the firewalls providing sort of intermediate feedback, which tells an attacker whether the packets are accepted or not by giving you some information. So from attacker's perspective, they can send probe packets to infer information. So in this case, firewall sort of is intended to be helping improve security of various enterprise networks, but unfortunately, it could be, in this case, it's mobile users. It turns out it can be abused by attackers' perspective to launch attacks. So this line of work resulted in a kernel, Linux kernel patch, And then we started looking at mobile systems, and we also found network information can be abused to create a UI-based attack. So it's all fun to look at these attacks, and then we thought about, how about defense solutions, right? So in the paper, usually we have some idea on defense, but that's sort of at the end of the paper, and then there's only one section devoted to it. So we started thinking, let's try to figure out a more rigorous approach to sort of eliminate these class of attack. How can we do that? So that inspired more recent work. So for one thing, we looked at Android systems, and typically a lot of work has been devoted to understanding security vulnerabilities associated with Android apps, right? Mobile apps. We all know apps are very popular, but turns out the operating system always has new features, and a lot of developers work on these operating systems. And there are these inconsistencies which lead to vulnerabilities. If the OS is insecure, then there could be more serious attacks that can be launched. So another aspect of the work is the focus of this talk is looking at basically packet injection attacks, this kind of TCP hijacking attacks. Can we eliminate this class of attacks completely? So how can we do that? So we are designing this tool, and this work is, I would say, want to thank my collaborators. Actually, is a student of mine, PhD graduate, who is now at UC Riverside. So I guess it's a grandchild of your Randy's. So, so this is recently presented in CCS 2015 this year. So I just want to give you some highlights of this work without going into a lot of technical details. Of what we think is a very promising research area is applying programming language techniques, in this case, static taint analysis, which is a very old technique. But unfortunately, it's not really a tool that's readily available. At the time, we're thinking, let's do taint analysis to look for these kind of attack. But unfortunately, the tools we identified, which are open source, this goes back to the open source discussion. I think the PL community has not really developed those kind of tools that handles large software code bases. In this case, the Linux kernel, the TCP implementation in the Linux kernel. So part of this effort is purely engineering, I would say. It's just developing the tool, making sure our static analysis tool can work on a large code base and would be efficient. And it's also reasonably accurate for the purpose of identifying these vulnerabilities. So let me just give you a brief overview of what I mean by packet injection attacks. Not all of you here have this networking background, but the idea is fairly simple. So there's a user, and let's say it uses either a computer or mobile device. It doesn't matter in this case. And it's talking to a server. Typically, it uses TCP, and HTTP runs over TCP. Most of these apps today actually use HTTP today. And obviously, you say that sometimes, most often, they use a secure version of HTTP, which is HTTPS. So let's start with HTTP for now. So an attacker who's not on the network path is interested in injecting spoofed packets, basically packets that should not be recognized as part of TCP connection. This obviously is bad, and we assume that the attacker is not on the network path. It's not a man-in-the-middle attack scenario, which is a less common approach, a less common threat model that you're assuming someone is sort of on your path. For example, your ISP is man-in-the-middle. It can do various things. But let's assume the attacker is not on the path. It's an off-path-based attack. So in that case, the attacker has to guess, right? For example, the TCP packet has to be in the right sequence number window in order for this packet to be accepted. So if it's able to succeed in this attack, then it can do things like phishing, can inject JavaScript, can do cross-site scripting, and so on and so forth. So that would be really bad. So what we want to do is to to prevent this kind of class of attack altogether for TCP implementations and other networking implementations. So obviously, we can have application layer security, SSL, TLS. And in that case, would you say that the attack is completely eliminated? Just a show of hands, who believes that this attack, this packet injection attack, will no longer work at all? Okay, so turns out that's not entirely right. So for one thing, okay, so first of all, there's low coverage of deployment, HTTPS. And secondly, the first HTTP request is still, the packet of HTTP request is still vulnerable to hijack. And a lot of times, it is starting with an HTTP right before it needs to do SSL handshake, and it needs to do, before that, it needs to do TCP handshake. So the TCP three-way handshake can also be susceptible to this hijacking, packet injection hijacking attack. So HTTPS does not solve the problem completely. And furthermore, you can have a way to reset the packet. So it's not really about injecting the data into the packet stream. It's also about potentially launch denial service by making the reset packet be accepted as part of the TCP communication. So basically, this shows you that packet injection attack is really important to defend against. Just higher level application layer or network protocol layer encryption doesn't really completely solve the problem. So given that this is an important problem, what we want to do is first survey what's already been done. Obviously, there are these RFC recommendations on what the protocol implementation should do to prevent this kind of class of attacks. But unfortunately, the actual implementation may not always follow these recommendations precisely. And even with the Linux implementation, what we found is that both Linux and FreeBSD, they found to be much weaker than the RFC, what RFC recommends, right? The RFC recommendation is one thing, and protocol implementation, the implementers may not exactly follow the recommendation. And we found that there is a way to perform fast sequence number cracking, basically inject packets, guess the sequence number in a very short amount of time, and be able to succeed in injecting the traffic. And so this motivates our work. So our solution, the PacketGuardian, as I alluded to before, is really relying on some programming language techniques, analysis techniques, to really exhaustively try to look for these vulnerabilities and identify ways to patch it. So our output will also give you information on how to how to create the patch for the protocol implementation. So the technique is trying to do static analysis, as I said before, and it helps us evaluate the robustness of the protocol implementations. So there are various implementations out there. For example, for RTP, there are multiple different implementations. And we can just run this tool, and this tool relies on this precise context, flow, and field-sensitive taint analysis with point analysis. You don't need to know the details, but these are not really novel techniques, but these are well-known techniques in the PL community. But we realize this is important to have in our use case of applying it to understand security problems of network protocol implementations. So one important thing is that we actually also focus on implicit flow analysis rather than the typical explicit flow analysis. It turns out that a class of this implicit flow analysis, which can be influenced by attacker-controlled input data, can lead to these type of packet injection attacks. So I will give you some example in the later slide. And in order for this tool to be very scalable, we use a summary-based approach to make it work well for large code bases. And that's really important because we found these previous approaches do not scale with large code bases, for example, the Linux kernel. So, and our assumptions are we do have access to source code for now, and the tool is just is a limitation to be able to analyze the code base. In this case, we are working with C++. And we have evaluated this tool on 6 real implementations. And just to give you a quick overview, we did find some of these previously unknown ways to exploit known vulnerabilities. So in other words, there are known ways, there are these known vulnerabilities to these protocol implementation, but there are different ways of exploiting it. So our tool is able to uncover all these different ways, the new ways to exploit these vulnerabilities. Okay, so I want to just give you an illustrative example of what I mean by this implicit flow analysis. So, for example, for network traffic, what you are interested in is when you accept a packet, you want to analyze whether the packets should be accepted or not. And from attacker's perspective, it wants to understand what is sort of way to inject packets so that this packet coming from the attacker would be accepted as a packet that it actually sent from the sender of the communication. So there are various checks that happen along the different code paths, and eventually it reaches accept packet function. So once that reached, that means the packet is accepted, right? So attacker tries to figure out how to send packets in such a way that it reaches that accept packet function. So that's sort of the high-level idea. And once it's accepted, it copies the payload to the upper layer, so this can affect the application, or it can terminate the channel and cause denial service attack. So the accept path is, if it's weak, then a vulnerability is identified. Okay, so that's sort of the goal of this static analysis, is to look for these weak accept paths. So in this particular case, let's say the path is weak, and in this case, it's weak because it's comparing to a constant value, right? So with a constant value, what you can do is you can guess, you can do sort of guessing. And usually the comparison, the checks, has to do with some internal protocol state. For example, the sequence number information, which is a secret piece of information of the given TCP connection. It's not directly available to someone who is offline, off path, right? So in this case, what we do is we look for these accept paths and try to understand whether the checks along the path are sufficiently strong, whether attacker is able to guess it. Yeah, and then we check for whether these protocol states are, if it uses some protocol state as part of the checks, whether it's difficult to guess. Okay, and so in this case, one example is that the packet sequence number you receive has to be within the window of what you expect based on the previous sequence numbers you have observed. And similarly, the acknowledgement sequence number has to be within this window of send next. So these are the two internal states, and obviously just randomly guessing it is 2 to the 32 guesses. That's just not feasible for an attacker to launch this attack. So the question is, how can this protocol state be leaked to the attacker? So this is where the implicit flow analysis comes in. And typically, what people think is implicit flow is not really exploitable. It turns out if attacker can influence the state, the implicit flow analysis can be exploited. So that's what we identify. For all these recent TCP packet injection vulnerabilities, actually exploit this kind of implicit flow analysis. So, for example, if it's able to trigger a public event like a storage channel, like a proc file, the proc file system stores information on the network stats of how many packets are received. So if you can just get that information, and based on that, you can attacker can infer. In this case, I'm assuming there's some attacker on the user's device, and you're just passively observing the information without special privileged access. And with that, it can give feedback and give the attacker information on whether this sequence number is within range or not. So that's just sort of the high-level idea. And with this binary search, it's much more efficient than guessing on the 2 to the 32 sequence number space. So, and with this approach, you can crack the TCP sequence number within 1 second, which is fairly effective even for a short-lived connection. So, so in the interest of time, I'm not going into details, but what we found is even some of these existing attacks looking at strong SCD-based leaks, which are focused on comparing with the constant value. These are ways to, for example, extract crypto keys on cloud servers, or trying to look for side channel leaks on web and Android applications. Those are much different from the implicit flow analysis we are doing here, because they are looking at a comparison to a constant. This is the strict control dependency leaks. So, so basically what we found is there's this attacker-controlled implicit information leaks that could be exploited, because attacker can control the input data to be able to get this feedback. And turns out this can lead to basically a class of these vulnerabilities of packet injection. So essentially we developed this tool to look for these weak accept paths and use, if the accept paths take into some protocol state for the comparison, for the checks, then we can do this leak path analysis to understand whether attacker is able to influence the protocol state in a smart way. So this leads to basically a set of patches for the vulnerability identified. And essentially we developed this static taint analysis, and I'm not going into details since I don't have a lot of time. So basically we applied the static taint analysis to both looking at accept paths constructor as well as the leakage protocol state analysis. So there's quite a bit of engineering work that goes into designing developing the tool, but it was ultimately satisfying experience because we were able to develop a tool that actually works on real protocol implementations. So this is implemented, and we did the evaluation on 6 real protocol implementations for both TCP, SCTP, DCCP, as well as RTP. I don't believe DCCP is really used, but TCP, SCTP, and RTP are all used. A word about the performance. So right now it's not really highly optimized, but it takes about 8 hours to get. But after all, this is offline analysis, so we think it's reasonably acceptable. But further improvements, optimization can cut down the time further. But it's definitely a trade-off of performance and coverage. So we found a bunch of vulnerabilities that are previously unknown. We found with TCP, in the current TCP implementation, we found that you can have these 3 new attacks, new ways to exploit this, and this is actually validated in the lab setting. You can with only 32 packets, you can succeed in injecting traffic into a TCP connection. And we also found 13 new high entropy leaks as well. So all these have been reported. Even these are relevant to the latest Linux kernel TCP implementation. And with RTP, we also found a bunch of vulnerabilities. And one of them actually did not have any vulnerabilities. As you can see, different implementations lead to have different levels of security. They all claim they follow the RFC. So this shows that it's really important to have 2 automated analysis to validate, even though they say they follow RFC, it doesn't mean they are secure. So just quickly summarize, so basically this line of work is trying to apply some kind of formal techniques. In this case, it's programming language-based analysis to the networks to identify network security, address network security problems. In this case, it's packet injection attacks, and we're also expanding this analysis to other type of security problems. So with that, I'd like to conclude with questions.
So we have time for a couple of questions.
I have one question. So one of the challenges with analyzing C++ code is that it's not a type-safe language, and there's a lot of pointer arithmetic,
right.
Especially when there's parsing code. That is one question. And the second thing is, usually doing implicit information flow leads to a taint explosion because there's a lot of conditional checks in code. So yeah, how did you guys get around that?
So yeah, I skipped a lot of engineering details. So what we did is so one thing we used the summary-based approach that actually makes things a lot more scalable, and we're able to reuse a lot of this analysis code basically it has multiple steps. Some of the results can be reused in the follow-up steps, so it reduces a lot of repeated work, if you will, to speed up the entire process. But overall, we realized that it has to be we used basically context flow sensitivity to ensure that it's fairly accurate. So definitely there's a tension between accuracy as well as efficiency, but we were able to achieve this kind of balance in our implementation. Yeah.
So I'm tremendously depressed in a way about your talk, because these are the code bases that you analyzed were very old, looked over by a lot of people, and you found these vulnerabilities in it. And it's wonderful to start having more automated methods, but it seems that no matter what methodology you have, there's so much code we depend on that it seems like almost an impossible task to analyze it all in a reasonable, discover the vulnerabilities before they become, bad things happen to us. So what is your cause for optimism in working in the security field?
Yeah, that's a very good question.
Job security.
Part of the reason that we wanted to do this is that a lot of work in the security field, at least from my perspective, is focused on identifying new attacks. I mean, it's kind of exciting to look for new attacks, which is really important. But it's also, there are these known attacks. I don't feel people have spent a lot of effort in trying to make sure these new existing known attacks are fully eliminated. We have good tools of software programming practice to completely eradicate those. Buffer overflow is still a problem, right? So So what I'm hoping is that this tool, we plan to make it open source, and hopefully it will be part of sort of the development process, right? You add new features into the code base, and you can just run this analysis. And if we make it open source, the hope is that the community will also contribute to it. Yeah. So we talked to the PL experts, and they all agree with us that these techniques are not really new from the PL community's perspective. But unfortunately, there are no tools that's available. At least open source tools that we can readily use to analyze large software.
Okay, let's thank her one more time.